Um, yeah, so as was mentioned, the title of the talk is Quantitative Refinements of Non-Squeezing in Dimension 4. And this is joint work with three collaborators, Antoine Song, Umut Varolgunes, and Jonathan Zhu. And we just put up a paper on the archive this past week that you might have seen. So the first thing that I want to sort of say is, where are we starting? Well, the starting point is this very classical question of symplectic embedding problems. So if we take standard R2n, by which I mean just take this R2n with its standard symplectic structure, dx1 wedge dy1 up to dxn wedge dyn, you can ask the question, if I have two domains inside of R2n, you can ask when there exists a symplectic embedding from one into the other. So this is a very classical question. I'm sure most of you have seen this question in some form or another. And of course, there's an easy obstruction, which is that at the very least, if you preserve the symplectic structure, then you have to preserve volume. So at the very least, you need that the volume of U is less than or equal to the volume of V. Okay. So, one of the first results that you learn in symplectic geometry is basically this embedding problem, but when you talk about a 2n dimensional ball. So I want to note here that I'm using sort of notation which is a little bit more standard in the symplectic community for people who think about capacities. So here R is the radius, and I'm going to write b2n of pi r squared for something of radius r. That's sort of, how symplectic geometers like to think of life. And so we'll stick with that. And for that reason, we'll also talk about a cylinder. And here again, if we talk about a cylinder, pi r squared, then little r here is the radius. And so we have these two objects, a ball and a cylinder. And of course, the cylinder is this infinite thing. It has infinite volume, and the ball is this bounded domain, so it has finite volume. But the amazing thing is that symplectic geometry, and really, in many ways, the start of how I think a lot of people think that symplectic geometry is interesting, is that symplectic geometry actually sees more structure than volume. So that's encoded in Gromov's non-squeezing theorem, that there exists a symplectic embedding from the ball into the cylinder, if and only if the ball has radius less than or equal to the radius of the cylinder. So I've drawn here, I've tried to sort of squeeze my ball into the cylinder, and you see that I couldn't squeeze the ball into the cylinder. There's sort of these parts that are sticking out here, no matter how I try. Okay. So, there's sort of a lot of classical figurations on these things. And, since the workshop since this weekend is called Low Dimensional Topology and Symplectic Geometry, I just wanted to give a hint at at sort of maybe why I'm saying this here, if there's enough people who are low dimensional topologists, which is that I think there's probably some interesting sort of low dimensional topology features that one could consider here, in that classical embedding problems have a lot of structure to them. So I want to give this example of the Hofer conjecture. So we can consider here 4-dimensional ellipsoids. So hopefully 4 dimensions is low dimensional. We can consider 4-dimensional ellipsoids, by which I mean we're going to take the subset of C2 where, so we're taking this sort of weird normalization here. And the reason that we take this weird normalization, it's essentially saying that A and B are the areas in the 2-dimensional planes. So for example, if you want the ball of radius r, you should take this e pi r squared, e pi r squared. So this is, again, just sort of that usual symplectic. All I've done is I've sort of normalized this in the usual way that symplectic geometers would think about things. And what you can do is you can let, you can define a sequence for this A and B, which we call n sub NAB. to be the sequence with repeats of elements of the form am plus bn. So just as an example, if I take n1, 2, well, I start with 0. Well, depends. Probably you shouldn't start with 0, but okay. And then from there, there's one way to represent 1 as a sum of elements of either 1 or 2. But for 2, there's 2 ways, right? I could represent 2 as 2, or I could represent it as 1 plus 1. And for 3, there's also 2 ways. It's either 2 plus 1 or 1 plus 1 plus 1. And for 4, just to point out that there's 3 ways, I have 2 plus 2, 2 plus 1 plus 1, and 1 plus 1 plus 1 plus 1. Okay. So you write this ordered sequence, and you say that, and it turns out that one ellipsoid embeds symplectically into the other if and only if, term by term, one sequence is less than or equal to the other. So maybe this explains in part the normalization, why we're sort of looking at areas instead of just radii, because here we're just looking at, instead we'd have to put an r squared everywhere else. And the thing that this is really hinting at, the fact that this was a necessary condition. So the fact that this was a necessary condition is really due to Hutchings. And what these quantities really are their ECH capacities. So, okay. For the boundary of the ellipsoid. And so, in this sense, here there's a whole world of, once you start talking about ECH, you really are in the realm of low dimensional topology. And so I just wanted to bring that up to make contact with the fact that, at least classically, there's a whole, the usual study of symplectic embeddings very much has a lot to do with with low dimensional topology. Okay. So we sort of take a different tack and we ask the following question. So, okay, so the ball doesn't embed into the cylinder. And here we're just going to, essentially from now on, we're going to take little r to be 1, unless I forget somewhere, which is totally possible in this talk. Then, in fact, if I forget the normalization at some point, just either let me know or feel free to ignore, whichever you prefer. So okay, this ball, it doesn't symplectically embed into the cylinder when r is greater than 1, but we can ask, the question of, well, how much do we actually need to remove from the ball so that it symplectically embeds into the cylinder? So you can imagine, just again, if I removed sort of those regions from the ball, I just cut them out, I can say, oh, well, that's some region that I could have removed from the ball so that it embeds into the cylinder. And I'm asking, how large does that need to be? So, in coming up with this question, so I'll make a remark shortly, but the volume that you can remove can be sort of arbitrarily small. So for that reason, like, volume's not the right thing to talk about, even though that previous picture, it looks like maybe you need some volume to remove. So instead, you should think about the dimension of the region that you should remove. And so for that reason, it's worth considering what's called the lower Minkowski dimension of a subset of Euclidean space. And what this is so this is a little bit of notation, but essentially, if you think about what this is saying, it's saying you have some submanifold S. I mean, if it's a submanifold S, then if you look at the volume of the epsilon neighborhood, so you look at the volume of the epsilon neighborhood, then this volume looks like it has volume which is growing like epsilon to the codimension of S. And so what you can do is you can turn that into a definition. You basically say that the lower Minkowski dimension of S is precisely this power, this optimal power, such that the volume is growing in this way. So okay, so you don't need to necessarily have a submanifold, and so you can have fractional dimensions and all of these sorts of things. And so for that reason, there's this lim-inf and everything that's there. But in your mind, you should think, okay, if I have a two-dimensional subset, the volume of it is growing like epsilon to the k minus 2. So that's kind of a that's a way to think of dimension. And so, there's this obstructive question here. If we have a symplectic embedding of the 4-ball minus a set S, and it symplectically embeds into the cylinder, can we find a lower bound on the Minkowski dimension of S? And of course, the constructive question would be, can we find such an S which achieves this lower bound? So there's sort of a trivial bound, which is that there exists such an S with lowered Minkowski dimension 3, such that the 4-ball embeds symplectically into the cylinder. So okay, I'm imagining here that I've replaced the ball. I've replaced it with a cube. Hopefully that's okay. They're the same up to pointiness, I guess. And I want to embed this cube now into some cylinder. And so what I do is I get my scissors from the drawer, and I just cut along these codimension 1 walls. And when I cut them along these codimension 1 walls, now, just piece by piece, I can sort of transport them. I can transport them into the cylinder. And so, I have that because I'm cutting along these codimension 1 walls, and I'm in 4 dimensions here. In this example, of course, the Minkowski dimension of this smooth submanifold would be 3. So, in particular, this shows you that the volume of S itself can be 0 for trivial reasons. Okay. So our results are the following. So if we have the symplectic embedding where we've removed the subset S, and now we can symplectically embed into the cylinder of radius 1, then the Minkowski dimension is at least 2. So, okay, so on the previous slide, I said that we could find an example where we could find examples where we got 3. So this is not quite the same bound. But actually, it turns out that if R is less than or equal to 2, we also have this construction where what we do is we can take out a Lagrangian plane. So that's certainly 2-dimensional. We can take out a Lagrangian plane, and that will symplectically embed into an ellipsoid, the ellipsoid E pi 4 pi. And that certainly embeds into the cylinder, which, if you want, you could think about this as E pi infinity. So for R less than or equal to 2, we have that actually this bound is optimal for R less than or equal to 2, just by this explicit construction. Okay. So at least for the first half of, for the first bit of my talk, just because time is always too short to talk about everything that you want, I'm going to focus on the obstructive side. So I'm going to show you how we prove this obstructive side, and I won't talk about this construction, but I include it just to point out that, again, this lower Minkowski dimension of 2, it might seem like there's a gap in optimality between 2 and 3, which there is, but only for R greater than the square root of 2. And I think that's something that's pretty interesting, that we have this construction. So it's definitely worth pointing out. Okay, any questions so far? Okay, great. Looks like at least the four faces that I can see, mine included, look happy enough. So okay, good. Okay, so just repeating the obstructive bound here, which we'll focus on. What is our proof? Well, what we do is we actually take a modification of that non-squeezing theorem that was mentioned at the beginning. Okay, well, the 4-ball doesn't embed into the cylinder, and that's some kind of proof by contradiction. You assume that it does, and then you use some J holomorphic curve theory to obstruct that from having happened. Okay, so then I should talk about what's going on under the hood of non-squeezing and how we're using that. Okay, I guess for the proof of non-squeezing, I'm in particular not in 4 dimensions, like I said I would be. So okay, fine. Suppose that we do have a symplectic embedding of the ball into the cylinder. Okay, so I've squished my ball into this shape that I guess looks like the head of a rabbit or something. And suppose that it fits into the cylinder. Well, what I can do is I can compactify the region of the cylinder that it lands in. So it's bounded, and so because it's bounded, I can cut off the cylinder at some height, and I can say that now I'm embedded into a sphere crossed with a torus. So this is I'm just thinking of this as a torus, but it's a it's a torus of size k, depending on what the embedding looked like. But the relevant information is that the sphere that I'm embedding into, so I have this disk here, and this disk in the cylinder has area pi r squared. And essentially what I'm doing is I'm saying that that disk of radius pi r squared of area pi times little r squared embeds now into a sphere of area pi little r squared plus epsilon for any epsilon that I want to choose. Okay. So now what I do is, I need some way to study some sort of J holomorphic curves. And so I pick a compatible almost complex structure J on this sphere across this torus. And I want it to satisfy the property that on the region where I've embedded the ball, that the almost complex structure that I'm using is just the standard complex structure on the ball. So maybe just to go back for a second, I have this ball here, and it comes with its standard complex structure I. And all we're saying is, okay, well, whatever this phi was, we just sort of push forward I on this region, and then we can extend in some way through the rest of this compactified domain. Okay. So the key claim here is that for a generic choice of J, in fact, in this case, you don't need a generic choice of J. Yeah. So in this case, in higher dimensions, this is trickier. Well, no, you don't need a generic choice of J here. Okay, so that's not really necessary, but I'll leave it there anyway. The J holomorphic curves in the class S2, so those curves which are sort of going across, they actually cover X. So there's always a holomorphic curve which passes through any point in this compactified domain. And so, the picture here that you should imagine is, I have this J, and I can choose my J to sort of be, sort of standard near where I'm compactifying everything. So you can imagine that I have this kind of, there's always through any point, there's always some curve. So if it's out here, it'll just be a flat curve like this. But here, there's some curve that still passes through it. And the idea of the proof is some kind of deformation argument. You start with a standard split almost complex structure. And for the split almost complex structure, you just have these horizontal leaves going across. That's what the moduli space looks like. And as you deform, you basically have to check that there's no bubbling. And that's encoded in the fact that we have a sphere across the torus. There's only one H2 class, and we're looking at the lowest area one. So, okay. Now, a key remark here is, at some point in our proof, we should use the fact that we have dimension 4. And here's really where we're using it. So by positivity of intersections, if I have two two J-holomorphic curves for this almost complex structure, then they intersect in as many times as the intersection of the homology class with itself. So the sphere doesn't intersect itself. And so none of these leaves are going to intersect each other. And so this is actually a smooth foliation of the torus across the sphere in 4 dimensions. Otherwise, it's just a sweep out. Okay, so to finish up the proof of non-squeezing, there's one. You choose the J-holomorphic curve, which passes through the image of the origin, and so in the ball now that passes through the origin of this ball, and it's actually legitimately. So this is an I-holomorphic curve where I is the standard complex structure on the ball. Holomorphicity now implies that this curve is minimal, and because of compatibility of almost complex structures, you have now that there's an area bound. So the area of this curve, since it's minimal, is at least pi times big R squared. But its area, on the other hand, is bounded by the area of the leaf on the other side, which is homological by compatibility. It's pi little r squared plus epsilon. Okay. So that completes the proof of non-squeezing. And so again, just to repeat, in 4 dimensions, we get this foliation of I-holomorphic curves on this compactified domain into which we've embedded this ball. I mean, we haven't, because such an embedding doesn't exist. But okay, but if this embedding exists, we get this foliation. And you can think of this foliation in the following way. So you can think about it as a smooth function from the ball to the complex numbers. So just to sort of draw the picture, remember, here's our compactified domain. I've embedded this ball inside, and there's all these leaves. So there's like so there's the flat ones up here, and then they start entering, and they kind of do something funky, and then they're flat down here. What you can do is you can take the intersection. So you have that there's kind of a torus at infinity, by which I mean it's at infinity with respect to the sphere. And now I have a map, which is just from the ball to this torus, which is just for any point in the ball. I take, for any point in the ball, I just map it to, so for any point in the ball. One of these days I'll get used to technology. Okay, for any point in the ball, it maps to this point at which it intersects the torus. And again, by positivity of intersection, there's just a unique point on the torus for which this is the case, because the torus is itself holomorphic. And so they have these two intersect once homologically. Okay. And okay, the ball is contractible, so in the end you have a map to the 2 torus, but okay, fine. So that's really a map to the complex numbers. You can lift it now in any way that you want. Okay, so you just get a map to the complex numbers, or if you prefer, to R2. Okay. So actually, the same argument is giving the following. And here's where we start to see where this kind of defect, where we're saying, cut out this S, what do we actually get? So suppose that S is a compact set in R4. And suppose that we have, here's the hypothesis that we want, that we have a symplectic embedding of the 4-ball minus S into this 4-cylinder, but of radius 1. So from radius R to radius 1. Then what we can do is we can take U to be an open neighborhood of S. And I'm going to ignore what's happening at the boundary in most of what I say. So technically, the boundary can be, can go all funky. And so you should also take a neighborhood of the boundary, but okay, let's just ignore that. So we're taking an open neighborhood of S. And what we find is that there exists a smooth function, F, from the 4-ball now minus that neighborhood of U to the complex numbers. And it's, and not only that, this function has no critical points. And each leaf is a smooth, And in fact, each leaf is actually holomorphic, legitimately holomorphic, and its area is at most pi plus epsilon. So this is literally the same proof. It's just that instead of thinking of the ball as sitting inside of the cylinder, we're now thinking of this ball minus S as sitting inside of the cylinder. We take the same exact foliation and, and we just get this conclusion for free. So, okay, we have this function, and, at the end, all we do is we just choose a continuous extension of F to the entire ball. Okay. So we lose some amount of understanding what the fibers look like when we extend to the ball, but that's okay. So let me draw a picture. When I say draw a picture, I mean show a pre-drawn picture. So here we have our ball of radius 4. And of course, I'm saying that we get this. Okay, so right. So this region, this sort of inner region, what I'm imagining is that this is my open neighborhood U. So this is the neighborhood of U of, and there's some S. There's some purported S, which is lying inside of here. Okay. And what I have is that, okay, maybe I have, if I look at this leaf here, this leaf sort of, in this region, this leaf is actually holomorphic. But then, because I'm just taking any sort of continuous extension that I want, now if I look at what the pre-image of this of the same Z looks like, it's, it can do all sorts of funky stuff. I don't know what it looks like in here, but in the end, it does something, and then it pops out on the other side, maybe. I mean, there's not really another side, because remember, we're going to prove that S has codimension 2. But okay, so it sort of pops out somewhere else and extends to this leaf here. And again, just anywhere that's not in the yellow region, that's not in this U, we have that this is holomorphic, and hence it's minimal. And okay, we've lost control over U, over what happens in U, but nonetheless, we still have these leaves. So, okay, from here, there's 2 ingredients, and the first one is really something which I think I really want to point out, because I think here is where we're sort of applying a tool which hasn't really been applied in this way in symplectic geometry before. So, the key ingredient 1 is what's called the waist inequality. And so, let's just let n epsilon of x be the epsilon neighborhood of some subset x of a metric space, but all of our metric spaces are always are always balls or Euclidean space. So you can just think of like a legitimate epsilon neighborhood as you would think about it. I should make a remark that the dimensions in what I say are kind of irrelevant for the general statements in the citations that I include. But because we're focusing on 4 dimensions, I just want to say it for the case that we care about. So there's this waste inequality, which is due in some sort of in some form due to Gromov. Again, Gromov coming in with the tool that we need. And we're using a specific version here, which is due to Akopian and Karasev. So Gromov talks about sort of sweep outs of spheres and the areas of the leaves that are there. And here we really want to talk about a ball and some kind of, and not just the area of the leaf, but some kind of volume statement. So okay. So if I have a function which is continuous, which remember I do, then there exists some z, so some fiber, such that the volume of the epsilon neighborhood of that fiber is at least, and in this case, it's going to be pi squared r squared. So you should think about this as something like pi r squared times pi epsilon squared minus something that's little o of epsilon squared. So I just mean that as epsilon's going to 0, this is much smaller than epsilon squared. And so this first term is dominant. Okay. So, if you think about just the standard kind of sweep out, or the standard kind of continuous map, which is just, I take, I think about this as embedded in R2 cross R2, then of course, I just look at epsilon neighborhoods of the central guy. And the area of the central guy is pi r squared. And then when I take an epsilon neighborhood, it sort of looks like it's getting multiplied by pi epsilon squared. And the error term, because you're kind of clipping the outside, is little o of epsilon squared. So certainly for like the standard guy, this is true. And it's just the case that, all you need is a continuous function. You don't need anything about the smoothness of the leaves, nothing like that. It's just, you get this result sort of automatically. So the takeaway is that if we look at, one of the leaves here, the point is that one of these leaves has what we think of as a wide neighborhood, in the sense that we have that the epsilon neighborhood of this leaf is at least some value. So again, this leaf looks nice as it's traversing the ball, except for inside of this U, where it can be all wiggly. But okay, so there we don't really have much control, but okay. Nonetheless, this has a wide epsilon neighborhood. On the other hand, an older result due to Heinze and Karcher says that if we have a minimal surface, and again, this is a special case, if we have a minimal surface inside of R4, and now instead of considering the epsilon neighborhood, we consider the normal epsilon neighborhood. So what I mean is, sigma can have boundary. So sigma can have boundary. And the difference between, so here's my v sub epsilon, whereas if I wanted to take n sub epsilon, right, n sub epsilon would have looked like that. Okay. So I'm just taking this normal neighborhood. Then I have that the volume of this normal neighborhood is bounded above by the area of sigma, again, times pi epsilon squared, where you should think about pi epsilon squared as just the area of this fiber. So the takeaway here is that, okay, from ingredient 1, we found some leaf, say it's this leaf that I've sort of singled out. We have this leaf, which has a wide epsilon neighborhood, where we have a lower bound for its epsilon neighborhood volume. And at the same time, if you look at the portion where this is holomorphic, now you can consider the this sort of tube around it, this normal tube around it, and we're saying that that has a small epsilon volume for its epsilon neighborhood. Okay. So that's great, because now we can just define those, we can just combine those two things. So here, what I'm imagining is I have these two regions. So I have this region here, this inner one, and let's suppose that this is the epsilon neighborhood of so I set U to be the epsilon neighborhood of S to start. And I construct F with respect to this epsilon neighborhood of U. And then here, so this guy, this orange guy, this is now the 2 epsilon neighborhood of S instead. And so, okay, forgetting about what happens exactly at the boundary, and there's something to consider, because whether you're taking like sort of normal neighborhoods or non-normal neighborhoods, but okay, up to what's happening at the boundary. So maybe I just, you know, ignore this term. We have that if we look at the epsilon neighborhood of F inverse of Z, so that's this sort of blue, this kind of light blue highlighted region that I have. This is the epsilon neighborhood. Well, that's contained in this 2 epsilon neighborhood of S, because that's sort of the wiggle. Remember, you know, you can take the wiggly part, which is lying completely in U. And so the wiggly part has an epsilon neighborhood, which is completely contained in the epsilon neighborhood of U. This you should think about alternatively as the epsilon neighborhood of U. Together with this normal neighborhood of the portion of, so here, this is kind of the portion where the leaves are nice. So this normal neighborhood of the portion where the leaves are nice. And now you can just take volumes and apply the waist inequality and the Heinze-Karcher inequality. And so if I take volumes, I get on one side something that looks like pi squared r squared epsilon squared. On the other side, I have the volume of these neighborhoods of S plus pi squared times little r squared times epsilon squared. And that's just because, you know, we said the Heinze-Karcher was like the area of sigma times epsilon squared. Well, the area of sigma is at most pi r squared plus some error. So. And this is just saying that, you know, the volume, the 4 volume now of the 2 epsilon neighborhood is this thing. Pi is at least this much. And so the lower Minkowski dimension is at least 2, because the volume is growing like epsilon squared. This is precisely the definition of what it means to have Minkowski dimension at least 2. So I'll put a smiley face maybe. Okay. I should point out that, you know, you can play this game in a number of ways, where you can try to get this constant to be optimal, and that's saying not just you're not just talking about the lower Minkowski dimension, you're also talking about something called the lower Minkowski content, and so you can also play that game where you try to optimize this argument. So are there any questions about the proof of this obstructive statement? Okay, so just to recap, essentially what we did was we took the original non-squeezing proof and we said, aha, you get this foliation in 4 dimensions, and the only thing that mattered was basically that you had something that embedded into the cylinder, that embedded into a bounded region of the cylinder. And then instead of the monotonicity statement, if you think about what we replaced the monotonicity statement with, we replaced it with the Heinze-Karcher inequality. So, there's sort of one bound which is coming from that. And we have to use this slightly different thing than just the area of the leaf, because we sort of lose information about what's happening in this U. And then the last tool that we use is this waist inequality, which is actually a sort of, that's kind of a unique tool for this argument. So if there's a takeaway, I think it's basically the waist inequality. The Heinze-Karcher inequality is just a sort of natural extension of the monotonicity argument. Okay, so I want to just say for a second that from here you can easily discuss a slightly different version of this question, which is the following. So suppose that we have a symplectic embedding of a 4-ball into R4, and suppose that it has a bounded Lipschitz constant, L. Okay? Then you can ask, can we find a lower bound on the volume sent outside of the cylinder? And, of course, there's the constructive question as well, which is, can we actually realize this bound in any way? It's the same thing as before. It's just now we're considering an embedding of the whole ball, and we're bounding the Lipschitz constant. So the theorem that we've proved is as follows. On the obstructive side, at least, is that if you have such a symplectic embedding, then the 4 volume of this defect region. So this is, what do you think? This is the region S. This is the region S, which lands outside of the cylinder. Then the 4 volume of this region S is at least some constant, depending on R, divided by L squared. Okay. And this essentially follows as a corollary of the Minkowski dimension result. The reason why is because what you can do is you can say, I guess I haven't left myself room to draw a picture, but you can say, okay, well, here's the cylinder of radius 1, and we have this ball of radius R. And so if I think about a purported symplectic embedding, there's going to be some bit that lands outside of the cylinder of, say, radius R plus 1 over 2. And so if I just consider a point that's here, then there's some ball, around this point, which is completely outside of the cylinder. And by the Lipschitz condition, that's some small ball here where the radius of the cylinder of this new ball is multiplied by 1 over L. So I can sort of find a size 1 over L ball, which lands completely outside the cylinder. Oh, sorry, that's not exactly what I want to say. What I mean to say, what I mean to say is I consider the set S, I consider the set S that lands outside of here. And the point is that S has Minkowski dimension at least 2. So that's some S in here. And now, by exactly the same argument that I just said, that has some 1 over L neighborhood, which also lands outside of the cylinder by the Lipschitz condition. I see. So yeah, sorry, I didn't mean to say that we were just considering a point. I was meaning to say we consider this whole sort of S that gets sent outside of a larger cylinder. Okay. And on the constructive side, we can't get down to L squared, but we can get down to 1 over L. And, I should point out that, this means that if you allow your Lipschitz constant to get arbitrarily large, of course, you can have arbitrarily small volume landing outside of the cylinder. This is slightly different from what we said before because we're considering a symplectic embedding of the entire ball. But, that's sort of a result which is really codified in this fantastic result of Kotok, which in this simple case is somewhat trivial, but he sort of proved in 1973 a version of this for actually compact symplectic manifolds, which is very nice. Here, everything's in R4, so everything's you have a lot of room to move things around. But the idea is, again, you just chop the space into pieces, but instead of just sort of saying, I can put these pieces into this cylinder, now what I have to do is I have to sort of separate all these pieces out and then Hamiltonian isotope them into the cylinder. So if you do that carefully, I think the picture is sort of maybe more clarifying than anything. If you do that carefully, so instead of just cutting and then putting these pieces in, what we're doing is we're sort of taking these walls, which are, so this wall is, you should think about it as 1 over L thick. And, you take some sort of Hamiltonian, which just sort of translates this guy, this guy sort of goes downwards and then like maybe eventually comes across. And this guy kind of comes upwards and eventually across. And so if you take just a sequence of Hamiltonians which do this, in the end, it's kind of easy to see just by construction that, these 2 points, so these 2 points, which are at distance 1 over L, now their distance is sort of, of order 1. Now they're order, well, really they're order R away from each other, I guess. But okay, the Lipschitz constant here is at least L times a constant depending on R. But nonetheless, I can still apply this Hamiltonian isotopy, and if I'm careful, I can ensure that the Lipschitz constant of such a thing is of order L. You have to be a little bit careful because you have to make sure that, at some point in here, you have to be careful that like you don't accidentally stretch too much. That's kind of the only thing that could go wrong, but okay, but it's possible to do. Okay. So I just want to end on sort of the outstanding questions that are left, sort of the most obvious outstanding questions that are left. We have a full section of our paper which is devoted to open questions because there's really a lot of them that one could say. But I just want to sort of say the most obvious ones, which are, for the Minkowski dimension question, we could ask, what happens in the case where this radius r is greater than or equal to the square root of 2? Can we actually bring these two bounds closer to each other? In fact, we conjecture in our paper that the Minkowski dimension, that the lower Minkowski dimension needs to be at least 3 when r is greater than or equal to the square root of 2. But of course, that's is greater than the square root of 2. But of course, that's not known. So that's a very interesting question. And for this Lipschitz volume question, we essentially what we've defined is this infimal volume loss function, this volume loss, which is just over all symplectic embeddings of Lipschitz constant at most L, what's the infimal volume that's sent outside of the cylinder. And as we said, our results show that we get the obstructive bound of order of 1 over L squared and the constructive bound of 1 over L. And our methods, explicitly have that the lower bound is something like order r to the 4th and the upper bound is r to the 6th. R to the 6th probably isn't optimal, but you can also ask this question for modified r. And there's this question of, can we bring these two bounds closer together? So can we actually understand what this function looks like? In terms of, it would be great in terms of L, which is really what we focused on in our paper, which bound is right? Is it 1 over L squared, or is it 1 over L? But of course, bringing the R exponent closer together would also be very interesting. Okay. Well, that's all I've prepared. So thank you very much for listening. Thanks again to the organizers for letting me speak, and thank you.